M1L39 is pretty much doing the same thing we've been doing, multiplying and factoring, except we're going to have the imaginary I involved. So we'll keep this kind of simple. We won't spend too much time here. You got factoring extended to the complex realm. And so remember, one of the things that we always look for is if we have an I squared, we want to replace that with a -1. So if we were to multiply this, notice this is a conjugate pair. And that simply means that if I got a plus version here, I got a minus version here. So if we multiplied this together, we would end up getting x squared, because first times first, and then the outsides you get negative xi, and you get a positive xi, and you multiply these together, you get negative I squared. Well, since these is a conjugate pair, this one and this one's going to go away, and we're going to end up getting x squared, and since this is an I squared, we get a -1, and a negative times a negative is a positive, so we get x squared plus 1. Interestingly enough to look, this right here is a sum of squares, which is what we're now going to be able to factor, which we could not previously factor. So if we did another one that looked just like it, again, first times first, that would be x squared, and then you get a -5xi, and then a positive 5xi, and then you get a -25i squared. Again, this and this cancels out, and so you end up with x squared plus 25. And again, just for notation purposes, our result is a sum of squares in that given piece. We're not going to look at C, so we're going to move on and look at exercises 1 and 2, where they tell us to not multiply this time, but go in the other direction, that is to factor the following. Now again, remember, if we look at this, we denote this as a sum of squares. Now, if this was a difference of squares, let's just say we had x squared minus 9, and we factored this, we would open this up, we'd say an x minus 3, and we'd say an x plus 3. But this is a sum of squares, not a difference of squares. So the only difference is that now we'll put an x minus 3i and an x plus 3i. Now, to demonstrate that that actually works and does what it's supposed to, if we were to multiply this back out, x times x would be x squared, and then you get a plus 3xi and then a negative 3xi, and you get a -9i squared. And so again, you could see that this one would cancel this one out, and then you get an x squared, and this is a -1. -1 times 9, you get positive 9. That checks what we did. That shows that placing these i's here work. So if we did number 2, again, a sum of squares, even though, yes, I argue the 5 is not a perfect square when you look at it, but we're going to factor it out anyway. So in this case, we'll put an x here and an x here, and because we need that I, we're going to put I radical 5, and then plus I square roots of 5. And so that would be the factorization of x squared plus 5. And so if you end up with a number here that's not a perfect square, you're just going to write each one down with a square root under it in order to accomplish that task. So as we continue, we look at exercise number 3. They want to know what are the solutions to x to the 4th minus 3x squared minus 4. So again, we're just going to factor this out. Does not matter that it's an x to the fourth. Since it's an x to the fourth, we're going to put an x squared here and an x squared here. Think of something that multiplies to equal -4 but adds to equal -3. So it becomes a -4 and a +1. So we can factor each of these. This is our traditional difference of squares, the x squared minus 4. So we open up a set of parentheses. We'll write x minus 2 and x plus 2. Now to address this one, this is a sum of squares. And so since this is a 1, the square root of 1, doesn't really do much. So we get x minus I and then x plus I. And so what are our solutions? Our solutions are x equals 2, x equals -2, x equals I, and x equals -I. Part B says how many x-intercepts does the graph of the equation have? There would be 2 x-intercepts. There are 4 solutions. We should mention that. 1, 2, 3, 4. That's because our lead exponent is 4, so we should have 4 solutions. That does not mean that we have 4 x-intercepts. In this case, we only have 2 x-intercepts, and that's going to be at plus or minus 2. These two don't actually cross the x-intercept. So C are the solutions. Our solutions to the polynomial p of x equals 0 have the same x-intercepts as the graph p of x. The answer would be no. Again, same reason. It's going to have x-intercepts at +2 and -2, but there are also 2 other solutions, plus or minus I, which are not x-intercepts. And so while we may have 4 solutions, we only have 2 x-intercepts, and that creates that little bit of a difference. So the last thing I'll show you is 2 problems. First, I'll show you A, and in this process they want you to write a polynomial in standard form for each one. So they give you here a set of zeros. We want to rewrite these zeros as factors, and then we're going to take those factors and then we're going to multiply them together. So if we have these factors, we would end up having x plus 2, we would have x minus 3, we would have an x plus 4i, and then we're going to have an x minus 4i. And we're going to multiply these together. So if you multiply the first two, you're going to get x squared, -3x, and 2x is -x, and then 2 times -3 is -6. This is a conjugate pair. It's also a sum of squares. So when you multiply that together, you're going to get x squared plus 16. And then we're going to multiply these two things together. So we'll get x to the 4th, because x squared times x squared. And then 16 times -x is -16x. When we multiply 16 times -6, we're going to get -90. Well, actually, I'm ahead of myself. X squared times -6, -6x squared. 16 times x squared is 16x squared. 16 times -x is another -16x, which I think I got confused. So let's actually back this up and let's multiply this over again. So x squared times x squared is x to the 4th. Let's keep with the x squared times -x is -x to the 3rd. X squared times -6 is -6x squared. Now we're going to go to the 16. So we're going to add, 16x squared, and then you're going to have a -16x, And then 16 times negative 6 is negative 96. We'll combine like terms, so there, we keep the x to the fourth. We keep the negative x to the third. We combine these two to get positive 10x squared. And then we keep the other two because there are no other like terms. So you get negative 16x and then negative 96. So that ends up being your answer. Now, so one thing we'll note before we go to part B is the complex zeros have to come in pairs. They can't work or stick around in isolation. So if that's the case, this is a negative 4i, there has to be a positive 4i. So if we were to look at letter B, we see a positive 3i, but what is missing is the negative 3i. We have to put that there because the complex numbers always come in pairs, opposite pairs for that matter. So if we solve part B, now the zeros would be, as the factors would be x plus 1, and then you would have x minus 3i, and then x plus 3i. So these two are conjugate pairs. They're also going to be a sum of squares when we multiply them, so we'll do those first. And that's going to give us x squared plus 9. So then we'll bring down our x plus 1. We'll multiply these together, so x times x squared is x to the third. And then you get plus 9x. And then you're going to get x squared. And then you're going to get plus 9. So if we write this in its complete correct order, it would be x to the third, and then plus x squared, and then plus 9x, and then plus 9. So these are the two most important ones, is A and B. I'm not going to do C, I'm not going to do D, and I'm not going to do E. If you're interested in that, come see me and we'll talk about that. Outside of that, the practice set is where you're going to go next. And so you're going to work on numbers 1, 3, 5, 6, and 7.